we're going to be solving a classification problem with, in the old days, this was a real problem. Now it's considered kind of a basic problem. But this is a so-called MNIST data set. It's associated with a bunch of character recognition problems. And we're going to use a subset of it that's only 10,000 images. And that is just for efficiency so that we can do this very quickly as we go through a notebook. Okay, so I've got my usual support code here that we've seen before for plotting. Now, here's the start of our difference. We're going to load from this sample that I've got in my on my website. That's just easy to get to, and I'm going to put it in X and Y. And these are NumPy arrays. As you can see, there are 10,000 images, and there are 784 features per image. And what that is from is a 28 by 28 image. So 28 this way and 28 this way, multiply it out, that's 784. So for each image, we're going to sort of flatten it all out into one long vector, and we're going to call that our feature vector. Okay, so just for fun, we're going to shuffle all these things so that they're not all grouped together and by digit or whatever. I don't know what's in there. I'm just going to shuffle it. And so there's a little routine I have called IMGrid that just displays the images themselves as well as the known truth associated with them. And some of them, these look okay. Sometimes you see some really weird handwriting, but these actually look pretty good. So if I ran this again, we'd probably see some other samples. So this is just sort of a standard way when you start a problem is to look at it, just see what the data looks like. And since I like to automate stuff, I'll make a little function here which you can look at. Right. Once I have the data that I've pulled out of that CSV file, I'm going to convert it into a bunch of tensors. So if you look at any one particular tensor, you'll see that it's mostly, depending on what image you're looking at, it's mostly, it looks like a bunch of zeros, but there's non-zeros in there. It's just really hard to find. Let's see. I guess I could. It's not going to show me too many. Anyway, those zeros are the white background. Okay, so as we did before, you usually want to have some kind of a baseline. We want a baseline that indicates if we're doing a decent job with the model we're trying to create. And a random forest is actually a really good model, so if we can beat the random forest, we're in really good shape. That's a very strong baseline. Often I'll use a linear model as a background baseline. So in this case, it turns out I needed quite a few trees in my forest, and we'll look at these in detail in the machine learning course. The number of jobs just says do it in parallel. And notice I don't really need a lot of hyperparameters here. I'm just saying make me a big forest and train. And sure enough, when I run the training accuracy and the validation accuracy, I get a pretty decent result without having to know very much. I don't have to know about neural nets. I don't have to know about much of anything, except that random forest classifiers are quite good. All right, so we're getting really close to 100% accurate on our validation set, which tells us that our model is pretty general. As we move from binary to K-class classification, accuracy isn't precise enough really because it's hiding a lot of details. For example, it might be the case that you're really good at predicting digit 9, but you're really bad at predicting, 7, because it looks like a 1. And that's something that you might want to know. And so you'll see something called a confusion matrix. And what this is doing, this is part of scikit-learn that I'm doing. So I'm taking my known truth from my test set, and I'm taking the predictions that come out of my random forest model. And down the diagonal, so when I equals j in the confusion matrix, that says I predicted a 0, and in fact it was a 0. I predicted a 1, and it was a 1. And so down here is what's known to be true, and across here is what we predict. So anything that's off diagonal is an incorrect prediction. So since I can never remember which are the columns and which are the rows. I made a little function here. And this function just creates a data frame that just so happens to use a little bit of LaTeX in here to get me a y hat. And so I set my columns to be, I predicted a 0, I predicted a 1, predicted a 2, and so on. And then here's the truth. So it was definitely, of the images that were 9, the true digit 9, I predicted 167 of them as 9. But some of them I predicted as, let's see, a 4 and a 3. I guess that's it. So this is, if you condense this down to just pure accuracy, you could do that, but then you miss, which ones you're really good at. And another way to do this would be to convert these to percentages. So this is 197 out of however many's in that. Let's see, I guess you think about probably the row. You'd have to think about how to convert that real quick. But so this is a confusion matrix is something I like quite a bit because it gives me a lot of details. And of course, you can do this for binary as well. And in the binary case, you tend to hear terminology like, false positive, true negative, things like that. I tend not to do that for a K-class problem. Okay, so we have a baseline. We're solving a classification problem where we have an image with a bunch of pixels, and this is just the raw grayscale value. And we're using all these pixels to get a prediction about which target it is. Okay, so how do we go from the binary to the K-class? Well, instead of having one neuron here at the end where we take a vector and convert it to a one vector, otherwise known as a scalar, we're going to get K neurons at the last layer. That just makes sure that we have a K vector at the end. And then rather than thresholding it with a sigmoid to get it between 0 and 1, we're going to use a softmax. So this is just my little symbol that indicates softmax. And that's simply saying, figure out the likelihood of each one of these different classes and convert whatever these regression values are. They could be quite large, could be 5 million. We're making sure they're all positive and between 0 and 1, and they sum to 1. And this tells us, if we look at the max of these, it'll tell us which one is the most likely based upon our model anyway. Okay, so how do we convert this to code? Well, we had this original, we have an input layer that takes the 784 features and converts it to a 50 vector. We run it through our nonlinearity, and now I'm sending a 50 vector into here, and I only have 4 here, but this is really, in our case, 10. So there'll be 10 neurons down here, so the result is a 10 vector. And these numbers are unbounded, they're just whatever. When I run it through the softmax, I'm going to get 10 numbers, and they're all going to be the likelihood of the various classes. Okay, so our model has to have this on the end. So instead of a sigmoid, we have a softmax. That's the difference in our model. Oh, sorry, and we're generating not a 1 here, but we're generating 10 different values, not just 1, because it's not binary. Now, in the training loop itself, we have one other difference. Instead of saying our loss function is a binary cross entropy, we just use the more complicated version, which is just plain cross entropy. Okay, so this is expecting these probabilities coming out of here. So you got to make sure this softmax is there, otherwise this cross entropy will give you a garbage. Okay, so here's our standard training loop, and here's our difference that I just mentioned. Other than that, we're passing all of our training data into the model to get some predictions. And because we have a softmax, then we know that these are actually probabilities coming out of there. And then here's our standard thing that tells our optimizer to move our model parameters in the direction of lower loss. So if we run this thing, then what we find is, as we expect, we're getting lower and lower loss here. I'm not showing the validation loss. We'll do that next. I just want to show you the simplest possible way to extend ourselves from the binary classification problem. Okay. Now, if we want to use this thing, once we've trained our model, we've got this model object here, and all of its parameters have been updated to be some good location that gives us a decent validation there. And if we want to actually use the model for something, for example, here, I'm passing all of my training data in. And so I'm getting the probabilities out for each one of those. I'm getting a matrix out that has the, in fact, look at the shape of this thing. So for 8,000 images, there are 10 probabilities. Each one has probability for each digit. So I'll leave that in there. It's probably useful. Okay, now if you want to actually make a prediction, you're not looking for just the likelihoods, then we use our friend argmax. And that just says, now this parameter is important. It's basically saying go across the column. So for any row, for all these 10 values, what is the index of the highest probability? And so that gives us the probabilities. And here, if I look at the first one and get it as a numpy vector, then you'll see one of these is going to be high. Yeah, so this is 0.99999. So this is going to be, this is 9, this is going to be 8. And sure enough, once I convert it to a prediction and the shape of these, there's 8,000 results because I've got 8,000 images. But the prediction I made for the first one follows from the fact that the 8th digit position is the most likely. All right, so now if we want to compute the overall accuracy, we're going to look at the predictions, the 8,000 values that we predicted versus the known truth in Y training. Now again, I'm doing this on the training set, which is not normally what we care about, but I'm just trying to give you the simplest possible example to do K-class first. Okay, so this gives me a Boolean vector. If I sum it up, it'll treat the false as 0 and the true as 1. And so that'll tell me how many are correct, just a count. And so I need that as a floating point number. And then I'm going to divide that by the total number of images. And of course, that gives me the percent that I got right. And you can see that we do really, really well, but we would expect that because we have a reasonably powerful model, and we're asking it to answer questions on a test for which it has seen the answers. And once again, I can use my little show matrix thing to see what this looks like. And notice that I'm not doing as well on the 9s as I did with the random forest. Okay, so now let's take a look at the validation accuracy. So now I'm going to run the, instead of xtrain, I'm going to run the entire xtest matrix, which has got a row for each image. I'm going to run that into the model. And actually, probably have changed these. Let's call that Pava. And of course, probably have to rerun all this stuff. Although this could be accurate. Let's see, test predictions. All right, we'll assume that that's accurate for a second. So according to what we pass into the model and what we're comparing, we get, training set or training error versus test error. So the matrix here gives us all the details that we want about, where we're performing well. So if these targets are, marketing buckets like, mountaineering person, or fancy dresser, or I don't know, whatever marketing people categorize humans in, you might go, oh, we're not really predicting well whether somebody's a fancy dresser, but we're pretty good about detecting whether they climb a lot of mountains. So this kind of level of detail could be interesting and useful to you at some point. Okay, so I think because I've kind of rerun this thing a whole bunch of times, these numbers here aren't particularly accurate, but I don't want to stop and rerun everything because it takes a while. Okay, so that was a training loop that is simply tracking the training error as it goes along, but let's update that so that we can now track the validation error as we go along as well. Now I've got the exact same model here. And so instead of just showing the training loss, I'm showing the test loss. And this is actually pretty good. We're getting that loss pretty low considering we're doing on the validation set and not the training set. So doing the exact same computation I've got from above, except now I'm doing it, just running it through again just to be complete. We're not perfect with this validation accuracy, but we'll see how we can improve that in just a second. And I've also got these functions, plot loss and plot accuracy. This is useful because you see the trajectory of the learning of your model. And in previous examples, we saw this thing diverge quickly. And so you realize, oh gosh, I don't really have to train that long because the validation error is just going to get worse. So let's just pick the best. I gotta get my chat line up here, sorry. Let's just pick the best model, or let's just train only for a short amount of time. In this particular case, it looks like, although we've asymptotically approached something, more training is a little bit better. Like if we stopped at 200, I think we'd be missing something. So having little tools like this, it just makes your life a lot easier as you learn to train these models. And I like to make my own custom stuff. It's a lot easier than looking stuff up on the web and seeing what other people have. But I have tried this thing, I can't remember, Google has something where it basically notifies this dashboard and you can see how your model is performing, but it connects to some dashboard over at Google. Okay. So let's try to do a better job. Depending on when or how the randomness is, depending on how your model is initialized, depending on the training and test set split that we've done, all of these accuracy numbers are going to fluctuate. But in general, as I've run this, I either didn't beat or more or less got the same result as my baseline. So I'm like, all right, well, then I wouldn't bother with a neural network, at least with this vanilla architecture, because it's not going to do any better. And I thought, oh, okay, well, let's try giving it more power and see if I can beat it then. And if it's the case, then it's worth having this extra power. So I'm just going to bump up the number of neurons. And yes, I could try more layers. And I actually did play around with the architecture a little bit, and I found that, this is more or less a pretty decent result. So I increased the number of neurons from, I think, what we have, 50 to 300. And I turned down the learning rate just a wee bit. And for 1,000 epochs, I ran this thing. This is maybe a little better than the baseline that we had with the random forest. I've noticed that my training error, I got that really low with all these extra parameters. I can really tighten that error. In fact, we can look at this accuracy this is validation, sorry. I could also show it for training, but you'd see that there's almost nothing wrong. So this is a pretty good result. It takes a bit to train, but mostly what we're running into here is the fact that we're getting really close to 100% accurate. And as you approach perfection, progress gets harder and harder to achieve. And we can take a look at our plot history here. So there's a link here at the bottom. Basically, we're never going to really tremendously outperform a decent model like a random forest when we're so close to 100% accurate. We need to do something different, and we need a different architecture in the neural network, and that will be something called a convolutional network. And Yannet, are you going to do convolutional?
Yeah. What I'm gonna do also, so that you guys know, is that I'm gonna devote 2 classes to images, and when we do images, we do convolutional neural networks, and I am gonna have 2 other classes to text.
Great. Okay. So the other cool thing about these convolutional neural nets is they're going to train pretty fast, because even though they're a little more complicated, they're doing a feature reduction where they're taking these raw pixels and taking it down to some very interesting features, but in a much smaller space. And so we train faster, and we're going to get a much better result. So it can do really amazing things, like it has these filters where you go, oh, is there any horizontal lines? Are there any vertical lines? What about lines at a 45? And then that becomes a feature. So the cool thing about these neural networks is, in general, they're the thing that is creating the features. Whereas when we do traditional machine learning, as you'll see in the machine learning class coming up, there's a lot of feature engineering that we as humans are going to do to improve the accuracy of our models. And neural networks seem to be pretty good about coming up with their own features, depending on the problem. All right, so this is the extension from binary class to K class. And the key is right here. Instead of a single neuron in the final layer, we have the number the same as the number of classes. And we use a softmax and not a sigma. So that's more or less it for the model. And then in the training loop, we use a fully general cross entropy and not just simply the binary cross entropy. Okay, any questions I can answer for you on that? So the way to learn these things is to, even if you start out by cutting and pasting and just getting a basic program that has all these little pieces, you can even take the notebook and just run it yourself, but tweak the learning rates, tweak the number of neurons. Try adding a layer. So that, adding a layer is simple, right? Cut, paste. Now we've got another one, except this number has to match this one. And then you can try it. And so I just added a layer trivially. And I don't have to change my training loop. I don't have to change anything. So that's how you get a feel for whether you need to decrease or increase the learning rate or number of epochs. And in fact, for the number of epochs, I look at my history. So it's about getting experience to be able to train your own models. And we're dealing with fairly simple data sets here and fairly simple architectures. But if you can't train these, then you're not going to be able to train and successfully model things that Yannet is going to present for
you. Professor, I actually have one question. So how is this deep learning random forest different from just the ordinary machine learning random forest model?
The random forest model is just random forest. It's a baseline I'm pulling out of scikit-learn. It has nothing to do with deep learning.
Oh, okay. I see.
Yeah, don't worry, yeah. It's a standard random forest classifier. I'm using it as a baseline to say, hey, because if I tell you, let's say I give you a model that's predicting, whether customers buy your product in a particular store, and I tell you I am 85% accurate. Well, I don't know, is that good? Well, there's two ways to look at that. If I'm beating a human, then that's good, because at least I'm beating a human. Otherwise, I'm stuck with a human. On the other hand, if a simple linear regression model, is 90% accurate, then you have to say, oh, you know what? My model's terrible, because even a linear regression model is going to beat that, or a linear classifier. So that's why I like making a baseline, because it helps me understand and answer the question, am I doing a good job?
I had a quick question about so in your, I think it's the second example in this notebook, you run the same model, but you also print out test loss.
That's right.
At any point, do you like optimize it all for the test loss, or do you just only focus on the training loss? Or is there anything that you do, like see when it starts going back up, that you stop the model, or do you do anything with the test loss?
I wouldn't call it optimizing on that. I would call it stopping when you're getting worse. But yeah, so we are optimizing on the loss function, which is a function of the training set. However, if you see generality getting worse, but remember, it can be quite noisy. We're not noisy right now, but we're going to get noisy. Say a moving average is starting to go up. If you see a trend going up, yeah, then you can stop. The other thing you can do is just train for a while until you run out of Amazon credits or you get bored, and have your model always, or your training loop, always track the best model. And then just let it run. And then you don't have to worry about it. There are definitely, like if you use the Keras library, it has this nice thing where you can say, hey, if it starts, it's a patience, I don't know, some kind of thing that says, if it's starting to get worse, then stop. And I think maybe the Fast AI library has something like that as well.
Thanks.
Mm-hmm. You have to be careful though, because I've seen multiple times, even on toy data sets, where your accuracy is going up, and then all of a sudden it'll drop. But then later it'll go even higher than it was. You get into some weird corner of features of model space, parameter space, and it kind of gets stuck in a bad area. But then all of a sudden it'll fall down into a low area, which means give you good accuracy. So it's tricky basing it on a moving average of whether validation area is going to get is getting bigger. Right, good questions.
Actually, I have a quick question. So,
sure.
What's the difference between Keras and TensorFlow and then PyTorch?
Oh wow, okay. So there are lots of libraries out there that will help you build neural networks. Keras is an interface on top of TensorFlow these days. I think it used to be standalone. TensorFlow is a computation graph that I don't find particularly easy to use. And I don't think a lot of people do. So they put this Keras interface on top that makes it a lot easier to build neural networks. So I think of them as kind of the same now. And there's actually a new product coming along that I think Keras will sit on top of. But and by the way, the Francois Cholet, I think is his name, his book on the Keras library, it's really good. The guy writes really well. I would take a look at that. But it doesn't expose, like it hides a lot of stuff. And in this program, we're doing kind of we're hoping to get a deeper understanding of these neural networks. And later, yeah, if you want, you can use Keras. But once you understand how to build a training loop, then you can do all sorts of fun tweaks to it and so on. Okay, so TensorFlow is a computation graph mechanism, and it also knows how to do gradients for gradient descent. Keras sits on top, and then PyTorch is a totally separate library, and which is the one that we're using here. And again, it's got linear algebra, matrix stuff. Also can run in parallel on a GPU, which we're going to be looking at next. And it's really just a different interface, but it's more used by researchers, I would say, whereas maybe Yannet can comment on this, but I don't think researchers use Keras so much.
I can add a little bit of that. So basically, like TensorFlow and PyTorch are very similar at this point. One of the reasons why people tend to go to PyTorch is that TensorFlow is a bit more difficult. Like the API is more complicated to understand. I found it awful. I think they are trying to simplify it and make it closer to PyTorch right now. And basically there are two competing products, and pretty much right now they're doing very similar things. One is being developed by Google, TensorFlow, and the other one is mostly developed by Facebook, which is PyTorch. People that in academia prefer PyTorch because they find it more flexible, kind of easier to use basically. And there is a lot of development basically on PyTorch. PyTorch people that like PyTorch think that PyTorch is winning the race against TensorFlow, but who knows? And Keras, yes, it's a bit easier to use at the beginning, but what I find is that I would like you guys to actually understand what we're doing. And by looking at all of these like training loops, you actually understand exactly what you're doing. And it's just kind of easier to have a conversation and talk about how to change your loop, change your model, and more than using a library that is more obscure and you don't get as much out of it, I think. The same with FastAI, actually. FastAI is a great library. And in the future, if you want to use it, that would be great. But right now, I think you first have to understand what is underneath. And I think it's difficult to use as well. So you need to spend a lot of time trying to understand how to use it.
And FastAI sits on top of PyTorch, right? Yeah. Okay, cool. All right. So, I definitely encourage you to try out this.
Let me just one more second. So basically, the main thing about FastAI is that the first model is very simple. So you just do it, it's great. But then you don't have any insight on how to improve it. And that's what I found with students before. They make a model, they have something they're showing, but then they have no idea, how do I actually get this better? How do I improve it with FastAI? Yeah.
Thank you.
Okay, so definitely in your infinite spare time, play around with the K-class classification problem, and that's kind of your stepping stone to solving more realistic problems. Although, as I say, in the old days, that was a real